The recording is started.
Good, got it. Perfect. Okay, welcome everybody. My name is Chuck O'Dale, and I have kind of a weird hobby of looking at impact craters. As a kid, long time ago, as a kid, you look at the moon and you're fascinated by the moon, and you think, what all those craters there, will I ever get a chance to explore them? So on this front page here, we got the crater Tycho. That was the main crater basically in the front of the moon. And I look at that and say, will I ever be able to explore a crater? And funny enough, you can. On this planet, there are piles of craters, I found out. On the bottom left-hand corner here, bottom right-hand corner of the image, is the Pingulate crater, aka the Chubb crater, the New Quebec crater. And I was a kid in 1950s in a black and white TV, and I saw this documentary of Dr. Mean from the Royal Ontario Museum. And he's got an expedition up there. He flew with, 10, 15 guys up there to explore it. And the main gist behind it was a geologist named Chubb. He thought that was a kimberlite, and he thought, we're going to be rich. It's going to be full of diamonds. Well, there's a long story here. I'll get into it later, but no, he did not find diamonds. It is a basic, a simple crater, and the Tycho is a complex crater. And I'll get into that. Look at the Tycho there, and there's a central peak. Now, just think of a raindrop dropping into water in slow motion. You see the crater evolve and then collapse on itself, and it's basically a little spout stick coming up in the middle. That's the central peak of this crater. At these energies, these velocities, at 14 kilometers a second, when these things hit 14 kilometers plus, you're looking at energy that is beyond even thinking about. So the rocks essentially act like a liquid. So as the crater bowl itself collapses on itself, it's totally unstable. You get this central peak effect. So, oops, page can't be found. Uh-oh, we just had a crash here.
Yeah.
How did I get into this?
This might be an old link, yeah. There.
We'll get back to it.
So just the next tab over here.
Okay.
For the people arriving, there is pizza at the front if you want to go for that.
Technical problems here.
Let me just drag that out of the way.
There we go. Whoop.
The entire thing is gone now.
Welcome to Carleton.
There we go.
University.
There we go.
So who is this guy? Let's see if I can get rid of this guy. Who is this guy? I'll give you the 60-second elevator resume. I joined the Royal Canadian Navy back in the 1960s. I was a technician, electronic technician, learning the electronic high-tech avenues of voltage and vacuum tube technology. I was troubleshooting, bobbing around the ocean, learning the troubleshooting method. Now, fast forward 33 years, here I was troubleshooting microelectronics using an electron microscope, as in this image here. So in my career, I've gone from decimeters troubleshooting vacuum tubes to nanometers troubleshooting microcircuits. So if I could do that in my third-year career, I just imagine what you guys are going to have. Who knows? It'll be interesting. I just hope I live long enough to see most of it. So, here we go again. What's going on?
So top left there.
Top left. There we go. Lifelong dream. So, being in the high tech, I was fortunate enough to own an airplane. And with the airplane, my main hobby was exploring impact craters, all in North America and only on this planet, unfortunately. As you can see, I made it to the Pingulate crater. So this is the crater I saw in the black and white TV, and I said at the side of Dad, I said, Dad, can we drive there to see this crater? And obviously it's way up in northern Quebec. No, it didn't happen. So Dad, I finally saw it. I'll get into the technicalities of it later. So how do we identify an impact crater? Well, I'll get into that in just a second, but why are they almost always circular? That is the question a lot of people ask. And you intuitively you think it's always at a 90-degree impact, but it's not. You're looking at an object going at 14 kilometers minimum per second, up to maybe 70 kilometers a second. Imagine the energy when it impacts something. Essentially what happens is like your thumb going at the cookie dough. This thing will impact and vary itself. This, I'm talking picosecond here. And the energy that it takes to stop this object going this velocity to zero causes an explosion. So whichever angle this thing impacts, the explosion will always cause a circular object. The exception is when you have an extreme angular, almost a skipping motion. You'll get an oval crater from that. I'm just going to mention, we'll have a question and answer period at the end, long time. But if anybody has a question, please just let me know. So, and how can we identify an impact crater? So simple, eh? You get a circular structure with a crater rim on it, and sure enough, it should be an impact crater, right? Well, I'll give you some examples here. Here's 4 structures. The top 2 and the bottom 2 kind of look alike, don't they? 2 of them are impact craters and 2 of them are not. So I will with the laser. This here is the Brent crater, and this is an impact crater. This here is just a geological structure that looks almost the same as that. And coincidentally, they're within, say, about 80 kilometers of each other. It's the craziest thing. Bottom left image here is the Presqu'île crater. This is actually the bottom bowl shape of an impact. You have to imagine about over a kilometer of basically land from before the impact. So the impact caused this bowl, and over the years, the millions of years, we'll get into the age later, caused the erosion. So what you have is the bottom of the bowl of the crater here. And we did find a lot of basically evidence saying that yes, it was a crater. Now, raised rims around a circular structure. Yes, there are a couple, but as we say in the engineering field, it's low-hanging fruit. They've all been discovered. The one on the left here is actually it's right over. Yeah, that's the Chubb crater that I explored. Again, you can see the crater rim itself. And over here is the Barringer crater in Arizona. And again, there's the crater rim and a bowl shape. So these are 2 examples of yes, there is a bowl shape, and yes, there's a crater rim, and yes, it is an impact crater. In the center here is a circular lake that had a perfect crater rim on it. And this is the rim that I was on. That vertical branch of birch there, I was holding with my fingertips vertically, so the gravity would hold it vertical. And you can see the angle of the crater rim itself. That's what we climbed down and climbed into. We had metal detectors looking for meteorites, and no, we did not find any. So there is absolutely no evidence of the fact that this is an impact crater. It is a circular structure, and it's probably well, there's a long geology thing. And if you want to find out more history, go into my website, please. I could talk a day about this one. So how do we define what is the evidence for an impact? So this will be on the exam. The first example is a shatter cone. Now, I've got an example of a shatter cone here. And after the lecture, if you want to come over and take a look at it, what happens at the impact at these energies? What you have is melting, pulverization, and then shattering of the rocks. And when the rocks shatter, they shatter with this kind of pattern on it. And the pattern can only be caused by the energy from an impact or a nuclear explosion. So if you find a shatter cone, it is probably an impact, because a million-year-old atomic explosion might not be in the cards. Meteorites, again, is evidence. There are, we'll be getting into this later, there are two craters that had lots of meteorites on them. The one previous, the Behringer crater that I showed you, this is the meteorite from that crater. And so when we looked for that circular object before and we're looking for meteorites, no, we didn't find any. But if we did find meteorites, we would have been famous. We could have named the crater after ourselves. But we didn't. We didn't find any meteorites, but we found documented a nice circular structure. On the right here is what's called breccia. If you notice the rocks inside that rock, they're tiny shattered rocks. They're very angular. It's almost like a conglomerate, but a conglomerate is almost a glacial deposit, and the rocks are very rounded and eroded. And basically, it is not an impact, but the breccia with these sharp angle rocks, notice the very sharp angles here, all of them are different, and different rocks within the breccia. They are caused mostly by impacts, but unfortunately, there are geological processes on this planet that will cause a breccia that looks like that. So that is not the sole evidence, but a circular object with breccia around it would be a good possible example of an impact. On the bottom here, on the left, is a shattered rock. In the background, you look, see that raised hill over there? That is the crater rim of the Pingulet Chubb crater that I showed you just earlier. And these are rocks that were actually shattered from that impact. This is the only bedrock I could find walking around the crater that had this shattering effect. There are other craters that have this effect, and I'll document them later. The one on the bottom middle here is called a planar deformation feature. And you're looking, these are microscopic features that you require a very high speed or a high magnetized microscope. These are the striations within the quartz is only caused by extreme pressures from an impact. So quartz that are pressurized by the microscopic picosecond impact from a bolide would cause features like this. And this is firm proof of an impact, but the proviso is you have to find this in situ. It could be blown off from somewhere else, landing in another lake, and you say, oh, I found something, but you have to prove that this planar deformation feature is in fact from that structure. On the bottom right, notice I got my foot there for scale. On the bottom is bedrock, that's normal bedrock, and here is this black line of rock. It's called a pseudo-tachelite.
No.
And during an impact, this is from Sudbury, and this was about a 300 kilometer wide impact, big bowl, caused all these rocks, when they shattered, they didn't shatter apart, they very quickly rubbed to each beside each other, causing a molten effect for microseconds, then hardening. So what you had is the bedrock that at the bottom, that's what it originally was, hardened into that called a pseudo-tachelite. A tachelite from volcanoes is natural. This is pseudo-tachelite, not from a volcano, from an impact. Only two structures on this planet have this feature. One is in Africa and one is in Sudbury. And then final on the bottom right there is an impact melt. And it is very difficult to identify an impact melt, being a non-geologist. But if you notice that this rock is much different from the bedrock around, it would be a good, how should I say, a forwarding effect to say that this could be effect of an impact. So these are all signals that, yes, you might have had an impact, but the definite one is the shatter cone. And as I say, later on, take a look at the one I have here as an example to give you what to look for. These striations are very unique only to shatter cones. But there's one more thing that is an indicator of an impact, but it won't tell you exactly where it was, called tektites. These are molten globules that were ejected ballistically from an impact, and it could be hundreds or thousands of miles from the original impact itself. And the shapes of them here are documented. And the strewn fields from various tektites caused by impacts are documented here. The one in blue on the right-hand side here, we'll get to this later. This is a great mystery, which I'll describe to you at the end of the lecture, just to keep your interest peaked here. So let's get into some craters. This is the Barringer crater down in Arizona. That was one of the ones that is the first ones, beside the Chubb, I had to go see this one. So looking at it, you say, well, is it circular? If you look at it closely, it's actually square, isn't it? It's called a jointed crater. And the reason it's jointed is that it landed in sandstone, basically fossilized desert. So when it impacted, it cracked the desert in a very unique angular method, hence the square shape. There are meteorites around it. This is again the meteorite from this crater, but the rock that it was impacted into was called the Coconut sandstone. Coconut sandstone. It's the same sandstone that's exposed at the Grand Canyon. The example on the bottom is a virgin coconut. It's just I picked it up somewhere, but the top one is actually a shock. It's shocked from the Barringer impact. So it's the same rock, same element, but it's shocked and it's got this sheen on it. So this is the only one in this planet I know of that has this kind of a shock effect on it. And on the bottom right there is a wreck of an airplane. Now that is not an indicator of an impact. Well, not of a bolide impact, but it's an airplane impact. If you look at the arrow there, there's a little dot in the inside the crater right here. What had happened, I'll describe it first. The crater rim is at 1 mile high elevation, basically 5,280 feet high. It's desert, very, very hot. And if you're a pilot, you have this thing called density altitude that is very, how should I say, difficult for an airplane to climb in because it just doesn't have any thickness in the air to climb. So what had happened here was a couple of airline pilots rented this 150, a Cessna 150, and thought, oh, we could fly inside here. Let's see what happens. So they got inside the crater and they found with the density altitude that they did not have enough horsepower to climb out of the crater. All they could do is circle within it. And they were at the stall angle they couldn't turn it sharper because they'd stall, and they couldn't do a shallower turn because they hit the wall. So they ended up strangling the airplane here. And they did live. They ended up in body cast, but they did live. So they say that if you walk away from a landing, it's a good landing. And well, they didn't walk away, so it wasn't quite a good landing. Anyway, that's the story of Barringer, but just remember jointed crater. It's a square crater. A lot of people don't know that. Oh, here we go. Oh,
I think the arrow keys might help avoid that.
Yeah, okay, that's here we go. Yeah. Okay, we'll get into Canadian craters. Now, we start at Quebec. Quebec has what's called the Canadian Shield. It's basically been scraped dry from the glaciers over the millennia. And every dot you see on that image here is an impact crater. And I've explored all of them. I'm going to document a few of them. But you would think, well, why isn't there this sort of magnitude of craters all over the place? Well, there is, except they're buried within kilometers of ground and they're very difficult to find. But since Mr. Glacier scraped everything off the northern Quebec, we could see these craters very, very clearly. So again, this is Pinglet way, way up here. So you can see the difficulty of getting up here. We actually flew to Kuujjuaq, just in this area, and chartered an airplane that actually flew into a little wee runway that's in there. And we spent a couple of days with a great expedition. It is the deepest lake in Quebec, actually. It is 267 meters deep. And as I say, Chubb, the geologist, tried to find diamonds, but couldn't. And Mean did not find absolute proof that it was an impact, but he proved that it wasn't a kimberlite. So the mystery was, we are very, very sure it's an impact, but we're not positively sure until we found what's called impact melt. And I mentioned impact melt is a indicator of an impact, and impact melt around a circular object is pretty well guaranteed proof that in fact it is an impact. So I have the shattered rock, the impact melt, and a circular lake with a rim on it. This was guaranteed proof that yes, in fact, it was an impact. To give you an idea of how big this thing is, see these dots all over the place? These are people walking around the rim. This is the group I was with. I was the tail end Charlie here. I was the last guy, but it was a great walk. It took us all day to get around it. Next one we'll show you is Mysticin, just in Labrador here. This here is a complex crater. I'll go back to the Chubb crater. Is a simple crater. It's just a circular crater without a central peak. And the complex crater has that basically cave-in central peak in it. So just to explain it again, when you have this large impact, what you have is the bowl shape is very unstable. It collapses on itself, squeezing in the center and causing the mountain in the middle. Just like a raindrop dropping in water, you get the crater and then the reflex. And this central peak is the reflex of it. On the right here is the cliff. This is all impact melt within the Mysticin crater. It's pretty fascinating to see.
We got a question.
Yeah, I'm sorry, go ahead. Yeah.
No, so the peak, now is that something that has formed like over time, or is that something that's happening like in the instantaneous time?
It's
like during the impact, it's everything's melting and then it like.
Yeah, it's a darn good question. I missed that. I had this explained to us by a physicist that studies these craters. And what happens is you get the bowl effect. It's totally unstable, collapses and pushes this in. And this happens in a microsecond.
Mm-hmm. Okay.
So when the dust clears, this is the shape of the crater for millennia. So getting back at the very, very beginning, I showed you Tycho crater. That's what it looked like within a microsecond after impact, or maybe a couple of seconds anyway. So, and the crater rim itself, you get slumping effects, and you might get a talus slope from it. And one of the craters I'll show you has a talus slope. So, yeah, and of course the impact melt. This was again the energy within a nanosecond caused this rock to melt this thick. That just blows you away how much energy this takes. So this is how wide, as we were flying into it. We flew down into it. It's about almost 700 feet from the rim down into the crater and back out. The clouds were pretty low, so we had to actually duck under the clouds to get out of it. But that's the width of the crater, and this is the central peak. What's left of the central peak close up, and internal to the crater is wall of breccia. This is all the those very sharp rocks buried within the impact melt. It again indicates positively that yes, this is caused by the impact. So all these dots here is craters that we know of right now. And the one I'm going to show you is Clearwater right here. This is the Clearwater craters. Now, up until maybe 10 years ago, we had thought for sure this is a double impact. It probably was an asteroid that split in half and impacted bang, bang together. But no, it's not. These impacts happened, 200 million years apart. The one on the upper right was the first one that happened 460 million years ago. And this is caused, this was dated by, oh golly, I won't, I'm going from memory and I won't say it because I'm going to be wrong. It's on my website how they dated this, but the dates are definitely different. So these are beyond a doubt different impacts. And there's another couple that I'll show you later that is coincidental. So if you're worried about having an impact hit you, move to Clearwater because chances of a third one hitting there is pretty dim. But now on the bottom image here, that's a Tranquility Base here where Neil Armstrong and Buzz Aldrin landed. And right beside it are two craters, almost exact same size as the Clearwater craters. So when you're looking at the telescope, you look at the, I want you guys to look at the Tranquility, Sea of Tranquility, and see if you can find these two craters and have a look at them. And now pretend you're actually on the Sea of Tranquility, looking back at Earth. And these craters, the Clearwater craters, will look to you exactly like Ritter and Sabine look on the Moon if you look at them. So just imagine you're on the Sea of Tranquility looking at the Clearwater craters there. They're almost the exact same size. And flying around it, actually I'll go back. This is where I took that picture right from here, looking this way to the rim. This is the rim between the two. So this is actually this again is a central peak that erupted up and then collapsed on itself, causing a circular rim. That's very, very seldom this happens. I think the dinosaur killer has the same effect underground. This is where I was right here taking a picture in the next slide, looking at it, and you can see the circular effect of the islands here. And this here is the rim between the two craters. And I would love to be able to walk along there and just collect some geology of that, but unfortunately, it's my visa doesn't go that high. I'd love to do it though. But yeah, that was we spent about 20 minutes. It took us a good 8 minutes to fly across the Clearwater crater. That's how big that guy is. It just blows you away. The energy it took to instantaneously make that hole in the ground. So we get into Manicouagan here. If you look at a map of Quebec, and this circular object here is definitely an impact crater. It's lots of proof. But it wasn't proved to be impact until maybe 50 years ago or so. This is a beautiful picture though from the space shuttle actually taking the ISS in the foreground and Manicouagan in the background. And here's me and my airplane taking the same picture, a little bit lower. But this is called a annular trough. It's called. Now, this is not the size of the crater. The crater itself is maybe another factor of 2 larger than this trough. We don't know the exact rim because it happened 214 years ago, and Mr. Glacier did a number 2 or 3 times over top of this thing. So the rim is long gone, but this annular trough. Now, what caused this trough is very kind of unique. What you have in the center again is a central peak. That's the central peak in the middle, and what you have around the central peak, it's all melted rock. But from the impact itself, you get pulverization, total evaporation, then pulverization, then shattering of the rock, and then breaking of the rock, and so on. So what you have around this annular moat here was a very, very fine pulverization of the rock that happened at the impact. And over the years, the glacier scooped that out. So you had what's called a circular valley around it. And the circular valley got filled with water because of the Manicouagan Dam here. This dam was constructed in 1970 to 80, I think it was, that time frame. If you look over on the right, that's what it looked like before the dam was constructed. And a lot of people from that hypothesize that, well, it has to be an impact crater. And then, well, of course, science says, well, prove it. And eventually we did. So, but that dam itself is worth the drive up just to see it. It's a good piece of engineering. So within the crater, this is in the central peak now. These are 2 examples of breccia. I'll tell you a story of this rock here. This rock here on the left is just a piece of bedrock minding its own business. And 214 million years ago, it got schmucked by this giant bolide. I'm not sure, it must have been a couple of kilometers across at least. So this rock went ballistically straight up in the air and then came down, plop into the impact melt. And the glaciers, of course, have eroded the top part of the impact melt off, maybe a kilometer worth. The glaciers have eroded away. So what you have now is this sharp piece of rock within an impact melt complex here. And this is a tuning for scale here. It's kind of cool. This is other pieces of breccia within the same area. I really like that picture. That's cool. This one on the right. Now what you have there, again, is rock that ballistically got blown up in the air, but this thing is the size of a school bus. So it landed in the melt, plop. They estimated it sunk at a rate of 5 centimeters a second within the impact melt. So, but by the time it got to that point, it probably sunk into maybe 1.5 kilometers of impact melt before it finally solidified. So that it's not very visible, but a geologist pointed it out to me. It's kind of cool. Exploring within the central peak. This here is an impact melt cliff, just like we showed you at Mistison. And I thought, oh, great, I'm going to climb up to there and see if I can just feel it, maybe get a loose piece off it. Well, this is the talus slope over the years that, the rocks fell off and made a slope here. And this is as high as I could climb, because every 2 feet I climbed up, I slipped back a foot. And eventually you get a rock, that's maybe 70 kilograms heavy, rolling by you. I thought, well, this is the last place in the world you want to get a broken leg, because I'm in the middle of nowhere. So I stopped there and took this picture. This is as close as I could get to that cliff. But after I took the picture, I looked down, and what did I see? I saw this shattered cone here. That was perfect. So I had to take a picture of that. And again, an example of sure proof that it is in fact an impact. So you got breccia and impact melt and the shatter cone, firm proof, of course, with a circular annular moat. And driving up to the Manicouagan crater, it's a long drive up to that. You see the rock kits themselves, they go from solid and eventually get into a shattered. So as you get closer to the impact, you get this shattered wall of rock. So that's basically a second example of shattered rock you have of it caused by an impact. And our adventure on the impact crater itself, this is my buddy Eric, and he is a professional canoeist, and if it wasn't for him, I don't think I'd be here. But we were in this area here, exploring the crater, and as we're getting out, it was a nice calm morning. It was first thing in the morning. We got out in the middle of the lake, and this 20-knot wind came up, and you're looking at maybe a 20-kilometer fetch straight down the lake. And Eric says, Chuck, I think we're in trouble. So we headed to this island here, and we're stuck on that island for days. Nobody knew we were there. We had enough food for a week, and of course, lots of water, so no problem. But to give you an example, well, a canoe full of rocks, what could possibly go wrong here? That was one heck of a day, I'll tell you. But it was funny. We were out there and we came straight in, and Eric was in the back, and he steered us right up onto the beach, and I just stood out, didn't even get my feet wet. Of course, I was soaking wet out there because of the spray and everything. So we had to, we got in here, and this is about an hour after we landed. We started a fire, dried ourselves off. And of course, we pitched our tent. The next morning, in about the middle of the night, Eric shook my tent. Eric, Chuck, wake up, the wind's gone. So within 10 minutes, we struck camp, and we were paddling like heck for the other side. So it was crazy, because here we were marooned, and within 3 hours, we were sitting there having bacon and eggs in some cafeteria. Kind of neat. Exploration at its best. Yeah, that was an adventure. I'll tell you, look at those waves. Geez, that was cool. Literally. Okay. And the next one we're still in Quebec. This is Lake Mistassini here. Again, Eric and I canoed all the way up to it took us all day to get up there. Again, this is a miniature, we think, complex crater, because we think that island there is, in fact, the central peak of the crater. And give you an example, this is the Gulf of St. Lawrence and the two craters here, Ilverlow and Manicouagan, we just saw. This is the central peak. This is the island just beside it, and it looks circular. That little coast there is circular. So that might be the crater rim. We don't know. There's absolutely no evidence of the impact on that island. But within this cliff on the edge here, as we flew over it, this is the cliff, the only cliff that's on this island itself. And we did land on his canoe. And fortunately, yes, we did find these shatter cones. So again, certain proof that in fact it is an impact crater. So for scale, that's my geology hammer here. So it's just wall-to-wall shatter cones, that cliff. And this is an example of breccia from the island itself. Again, for scale, it's a penny. So the sharp rocks again within that breccia. Very, very, very few examples of the breccia. We looked high and low and hardly found any. So where are we next? Oh yeah, this is Presqu'île. Now I showed you at the beginning, I compared that to Scudamata. Actually, just remember the lake I showed you that looked like that. That was Lake Scudamata, just to the west of here. It's along Highway 7. And it's actually a pluton. It looks almost exactly like that, but it's not an impact, it's a pluton. Pluton is just a glob of lava that erupted, and then a long geological story about that, but just remember pluton. But this one, in fact, is an impact crater and proof positive. Again, this was Ile Relou that we just were at, and now is Presqu'île. The impact is to the south of there. It's right by the town called Chibougamau, if anybody's wondering about it. Again, shatter cones. Now, here we are again in Eric's canoe. We're paddling in the lake way back in this area here, just thinking life is great, living the Canadian dream. And you wouldn't believe the black cloud that was just coming at us with at great rates of knots, just like that hailstone that happened here just a little while ago. So we paddled like heck to get to this lee of this island and just waited out the storm, discussing life, the universe, and everything. And Eric, joked at me, Chuck, I see a shadow cone there. I said, yeah, no big deal. But eventually the rain never stops. That the hell with it. I'm getting out, take a look around. First rock I picked up was this shadow cone here. It was kind of cool. So again, wall-to-wall shadow cones in this place. And on the upper right here is a piece of quartz that was in it. I was looking for striations, planar deformation features, but I did not see any. But again, on the bottom here is mafic, and the mafic bedrock, you see the shadow cone effect. And for scale, you can see Eric's finger here. It's, we did a good exploration of that, just going back. We actually canoed from this area all the way around here, and then up the river from these black shadow cones was about there. So that was a good day. There was a First Nation little village here, and they were amazed at how far we canoed. I said, "You guys didn't go that far." I said, "Oh yeah, piece of cake." And the final Quebec impact in Quebec is Charlevoix. Now, just to the east of Quebec City, just up to St. Lawrence. Charlevoix is actually a half an impact crater, and nobody knows where the other half went. Who knows? That some geological effect happened. The St. Lawrence River itself is a fault line, so I'm sure that's part of the story. Geological collisions and so on. This island that's right beside it has absolutely no connection to the crater itself. It's totally different from any geology here. But this shadow cone effect here where my finger is pointing, this was, maybe 50 years ago. The road crew were going through making a rock cut through a bedrock, and they saw these unique features, and they said, well, I've never seen this before. So they called some geologists in to see, well, what the heck is this? And of course, the geologist immediately identified it as a shadow cone. And then hence, you get this circular object with a shadow cone in it, definitely proof of an impact. This is me in the airplane here at the airport. And just give you an idea, this is the central peak of the crater in the background, and the inner ring of hills. So again, you almost have an annular moat around the Charlevoix crater. So just like Manicouagan, you had the central peak, the annular moat around the edge of it here, caused by the rock being pulverized as with the impact. So that one there is, it's a good, the other side of Quebec City. So it's a day-long drive, but it's well worth the the exploration there, because it just shows you how big these things could possibly be. It just blows you away. So we're going to head west now to Alberta. And the Whitecourt crater, this hole in the ground was, people knew about it for years and years. Hunters used that as a bearing, we'll meet you at the hole in the ground type of thing as you went hunting. And this new technology called LiDAR, which will take a picture of the ground, which eliminates all the reflections from the trees. And hence they found this hole in the ground that looks really like a crater. Well, it's circular, but is it in fact an impact crater? Well, yes, it is, because in situ, there are piles of meteorites all the way around it. It's wall-to-wall meteorites around it. Now, I'll warn you, it is illegal to hunt meteorites within a certain area of this crater. There's a big sign saying, don't do it. But anyway, we had permission, and we had guides and geologists from the University of Calgary to explain everything to us. And in fact, yes, we did find meteorites, these iron meteorites. And this was a very kind of unique crater in that the impact was rather slow. In other words, it was it's about 36 meters across, so divide that by 20. That's how the size of the bolide itself was maybe 1.5 meters across when it hit. So the energy caused the minor explosion, but it was slow enough that allowed it to distribute meteorites all the way around this thing. And one of the meteorites in the bottom image here is like a piece of shrapnel from an explosive shell. And we hypothesized that it's from the back of the bolide that was blown off when it impacted. And you can see the scale of the size of the finger. So the meteorite is very small, but it's an iron meteorite. I'll get into various classes in a bit, but just be aware that, yes, it was very easy to find because we had metal detectors going beep, 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 all over the place. Lots of unfortunately, there's a lot of barbed wire fences that went beep, beep, beep as well, but yes, we found it. And this is Jillian and I in the bottom of the crater. So what happens in the crater stays in the crater. So heading east from Alberta, again, I mentioned to you that yes, the country is wall-to-wall craters, but very, very few of them are visible. The Carswell crater up here, up in the north of Alberta itself, this is the biggest crater in, correction, in Saskatchewan. This is Saskatchewan here. This is the biggest crater in Saskatchewan, and it's buried within the sand within from the bottom of Lake Athabasca. We flew over the sand dunes here. It was fascinating to look at them. Of course, the oil sands are within that sand dune, but there's sand dunes all over the place going back here. So these craters on the bottom, Maple Creek, Elbow, and so on, they're all buried within the prairie itself, kilometers of soil in itself. So they were discovered by oil explorations, getting profiles, magnetic profiles, and so on, and drilling, and did find impact evidence by drilling down, but they're not visible. So I'm not showing them tonight. Just I can show you a circle on the ground. That's all. But up in the north here are two craters that are visible within the bedrock here, and just want to explain something. When Jillian and I were flying back, we up over the Arctic Circle, and we're flying back east to Ottawa. And around this area, here we are in northern Saskatchewan. There's nothing here, absolutely nothing here. And we had two very close mid-air collisions. The first one, we're heading east, and the other guy was heading west at the wrong altitude. Here's a beaver. And I'd say within 400 meters is when I saw him. I said, whoa. And I peeled off, and he went by. I called him on the radio, nothing. So anyway, that kind of shocked us. So, we calmed down after that, and within a half an hour, there's these little metro liners that fly into these airports in the middle of nowhere in Saskatchewan, picking up various prospectors and so on. So this guy dove out of the sky, maybe less than a quarter mile in front of us. This airplane, boom. So two close mid-airs within northern Saskatchewan. Now what happens there? Nothing. And here we are, too close. So in other words, if you're a pilot out there looking, always keep your eyes outside, not inside. So anyway, into Gal Lake here. This is, we think, is probably the smallest complex crater on the planet. It's very, very small. It's only 5 kilometers across, but it has a valid central peak. So that is the unique part of itself. And then Deep Bay on the other side is a perfectly circular lake. And this guy, Deep Bay is, he is 220 meters deep. It's the deepest lake in Saskatchewan. So comparing to Chubb, very deep circular lake, and a Deep Bay, a circular lake, very, very prominent, the fact that, yes, it is an impact. So we get, yeah, go ahead.
Did they name the lake before or after they found out it was this lake?
I don't know. I don't, the First Nations have a superstition about it though, because it's so deep. You know, when they try to fish, there's no fish there because it's so deep. And they have some kind of, they whistle, apparently the wind comes up, so they don't whistle when they're on the lake.
Is there a lot of wildlife in like lakes that are craters? A lot of.
Yes, yes, there are. Actually, the Chubb crater, it has a very unique, I think it's a pickerel. And they are all starving, these poor fish. They're long fish, but they're very, very narrow and skinny. And there's actually, the lake is pure water. There's absolutely nothing in the lake, no vegetation, no nothing. It's how these fish survive is unknown, but look on my website, and there's an example of one of those fish that's long and narrow, and there's no meat on them. But yes, to answer your question, yes, there are probably around the edge of clear water they did find, but in the middle there was absolutely nothing. Whereas on the other lakes, through Saskatchewan, the average depth of these lakes are about 50 meters at the most. But this one here is over 220. So yeah, it's good. So getting on. Oh, yeah. St. Martin, this is in Manitoba now. The map is kind of almost unreadable. This is Lake Winnipeg and Lake Manitoba. Beside each one, the craters right in between. On the bottom there is a profile they found just by using a depth sounding, the sonar and so on, getting the shape of the crater, and drilling. They did find evidence that in fact it is an impact, so definite impact. But here I'm going to go out on a limb here. This is Chuck O'Dale's hypothesis. Now there's a crater called the Chesapeake crater up in Chesapeake, and around the crater rim there are 2 rivers that come into it that veer by 90 degrees right on the rim of the crater. And I hypothesize this is the Dauphin River going up and then going east towards Lake Winnipeg, and it makes a 90-degree turn. And this turn is not what's the word? That the rivers
Oxbow.
meanders, yeah. It's not it doesn't look like a natural meander. A meander is almost like a sine wave, whereas this one isn't. So my hypothesis is the reason that this river made this quick 90-degree turn is because the crater rim from St. Martin is right there. I call that the Chuck O'Dale hypothesis. So if anybody writes a paper on it, that's what it's called. So going further east now into still in Manitoba is West Hawk. Again, it's a very, very deep lake. And again, deeper than any of the normal lakes around. And they found it's very, very unique. And I can't remember the evidence of, I think they did drill and they did find evidence in the bottom. And I can't remember for the life of me. I should have wrote it down in my notes and I didn't. But by drilling, they did confirm that yes, and in fact, it is an impact. And where it is, there's Lake Winnipeg there, the city of Winnipeg here, and this West Hawk crater here in Manitoba. So again, you can drive to it. It's probably a 12-hour drive to get to it. But one of these times we'll get there. If we're driving out west, we do. Every time I fly out west, I fly over, take a picture. So going further east is in Lake Superior itself is the Slade Islands. These, again, this is a central peak of a large crater. The crater is about the size, you can see the circular image I made in the bottom here. It's happened, 400 million years ago. It's a 32-kilometer wide crater. The depth within the lake is very circular. So it is, it showed you that's like the annular moat around Manicouagan, same kind of effect. And within the crater itself, there is lots of evidence. Central peak here, and on the shore, we're looking from the top of the hill just here to the north towards the islands. This is how wide the islands are. They're pretty big.
So
Yeah,
just on the slide back there, on the top right, the kind of formation we can see in the water, is that kind of reflective of what you're showing, like kind of hand drawn on the map, or is that just a?
that's just ripples on the water. It's nothing. The circuit, this depth part here is on the far side.
Okay.
So over there. So this is Lake Superior. And this here, no, it's just a reflection from various wind directions in the lake itself. And this here is an image we took of the large shatter cone. Now we think, and Slate Islands is the largest shatter cone in the world. This is the shatter cone here. And this white dot, that's me standing on the shatter cone. Kind of cool. And these are the rocks within the crater itself on the central peak, and you can see the shatter cone effect all over the place. And breccia, lots of breccia around. So circular lake, breccia with shatter cones, definitely an impact. So going further east, here we come to Sudbury now. Again, I showed you Clearwater, the twin craters. And I told you if you're worried about getting hit by a large meteorite, move to Clearwater. I'll also move to Sudbury because these are two impact craters that happen side by side. And the only thing coincidental about them is the space they're in. Wanapatai is right beside the Sudbury impact crater. And the depth is very circular. I think we have a picture of it later. But here, this here is what's remaining now. You're looking at 1.8 billion years of erosion and geological movement within the function of the province here. So it misshaped this circular here into just an oval type of thing. So, but this is the bottom of the Sudbury crater, and the width of it is, we think, over 250 kilometers across. So it is fairly big. Proof of it, well, within Wanapatai, there's the Wanapatai itself and aerial of it, is what's called a suivite. It's a kind of a fallback breccia. It's a breccia that basically got ballistically thrown out and brought back and then solidified later. And is almost firm proof that this, in fact, is an impact. A lot of people disagree that this is impact, and a lot of people say it is. So I'm saying it is, but we don't know for sure, I guess, this is the answer. But suivite is an indicate of a impact. And getting into Sudbury, this is the Sudbury igneous complex here, but the Sudbury crater itself, you're looking at, over 250 kilometers. And shatter cones from this impact are circular all the way around the Sudbury igneous complex. This is the highway coming into the complex from the south. So it goes down into the flat and back. These are the mountains on the north rim of the crater. And if we go back here, you see these hills here. This is kind of the north rim of the Sudbury igneous complex itself. So these are the size of the mountains in the background, pretty substantial. And here's me flying from the west to the east into the complex, from the mountains towards us here. And you can see it's mountainous, and then all of a sudden it's totally flat. And that's the bottom of the crater itself. Proof of it. This is the pseudo-tachyllite, Sudbury, and this other crater in Africa are the only two places on the planet that have this kind of impact evidence. Shattered rocks. So we have the Manicouagan, the Pingulet, and now Sudbury proof of the shattered rocks within the complex itself. A breccia on the bottom left here, and of course the shatter cone. There's the wall. If you have to tromp through the bush to find these shatter cones, but they're all over the place at Sudbury. Awesome thing. And coming further east, just north of us here, just north of Ottawa, is the Brent crater. This happened 400 million years ago. It's very unique. If you look at the geology around Ottawa, you see limestone and you see bedrock in various places. Well, just north of here, the limestone has been scraped totally off. It's all bedrock until you get closer to Ottawa, where you start to find the limestone cliffs. But on the bottom of this crater here, if you drill down, all you're getting is the old limestone. And what happened is the glaciers actually went over top of it and left the bottom part of the crater full of limestone. So the pH of these lakes are totally different from the pH of any lakes around. Kind of cool. So we did explore. This is the crater rim itself. You can see it kind of visible around here. I'm just over the east part of the crater rim there. And Lake Nipissing, just to show you exactly kind of where the crater is itself. Again, I mentioned if we wanted a tour of the crater, I would love to take a guided tour around, and we can actually find this little mini Grand Canyon within the crater rim. I found it, I think 15 years ago, and I know a lot of people have searched for it and can't find it. I know where it is. So if people want to know where it is, give me a call and we'll take a little tour. This is breccia we found within the crater, and they found in situ crater by drilling. So we know the fact that, yes, there is breccia within the crater. This here was a rock I found inside the crater itself. So I could say it's not in situ. Basically, Mr. Glacier might have picked that up from hundreds of miles away and dropped it in, who knows? So I can say it's breccia I found in the Brent crater, but I can't prove that it's from the Brent crater. And finally, coming up to Holliford, just to the south of here. Again, this is about a 2-hour drive from Ottawa. Very interesting little crater. From the air here, circular. Again, people were driving down into the crater and out of the crater for years and years, not realizing it, in fact, it was a crater, until geologists did do a lot of drilling and searching and finding impact geology within the drill cores. They had to drill for it because there's a lot, the rocks over top of this crater is all limestone. So the crater formed, then the limestone was deposited over top of it within an ocean. So therefore it's, it's totally buried. But crater shell itself is visible. This is top pictures from the bottom of the crater. And if you look to the west there, you can see the crater rim. And here I'm on the top of the rim looking east on the same road. So you see, go down and back up the other side. So that's inside the crater there. And this is the northeast side of the crater. Down it goes up and down into the crater itself. And now there's a home here. This I took this in a field before the home was built, but this is a good example of the crater itself. And we're on top of the rim. The rim is kind of like the Chubb crater and the Barringer crater. You can still see the effect of the rim, but it's again 500 million years old. It's pretty old. So I'm going to leave you with some mysteries now. 12,000 years ago, we had what's called the Younger Dryas event. Lots of things happened, and nobody knows exactly why. These graphs here, this graph shows you the methane in blue and the temperature in red. The difference, the major time difference versus time, it happened from 12,000 years, 13,000 years ago to 12,000. So basically a 1,000-year gap here. Something happened. The woolly mammoths around here totally disappeared at that period. And this is another hypothesis. There are 3 craters around here that we think are dated to that era. We do not know yet. The study is still ongoing, but we do not know yet. First of all, there's a Charity Shoal just it's in Lake Ontario. This here is Coruscant just by Sept-Îles in Quebec, and Bloody Creek over here in Nova Scotia. I flew over both of them. Charity Shoal itself is an aeronautical map. Holliford crater is just up here. This circle I made there, that's where the Charity Shoal is. And this is on an aeronautical map, and this square here depicts that there is a magnetic anomaly around here. Could it be caused by the crater? I don't know. But it's there, and the crater, some kind of structure is looking like that underwater, is in the same area. This is what it looks like with a LiDAR effect, sonar. And I actually flew over, and this is the only part of the crater I could see from the air. But basically, it's almost bedrock, like basically a scraped off bedrock. So we'd have to dive on it to see if there's any shadow cones in there or anything like that. Drilling is out of the question because it's in the Great Lakes and a pristine, we can't drill. So that's the end of that. Yep.
It's like the hypothesis that then leads into another question, like.
Yeah, sure.
How often is there like what material from the impactor stays there?
Yeah.
So is that impactor material that's influencing it, that hypothesis?
That will. Now, I showed you two craters that have meteorites around, Whitecourt and Behringer, both have meteorites around it. The other ones do not have, because the glaciers moved them all away. Anything that was movable can be moved. Now, when the bolite happens, it's totally evaporation. The energy just totally gone. But the element of the bolite itself might mix in with the impact melt, which will give an indicator of the type of the bolite it was. Clearwater has that kind of signature. So to get back to here, we would have to drill and actually get a sample, or even maybe drag out of an anchor and see if is there an impact melt in it. We don't know. All we know is that circular structure is there, and it is the almost the size of Behringer crater, and it's almost a kilometer across, so it is substantial. So could it be a glacial kettle? You know, the glaciers, when they melt, they have very high-speed water in it. It's like a drill. And if you go to a place called Warsaw, just by Peterborough, there's called the Warsaw Caves, and it's just full of kettles where the glaciers have just drilled down. And it's just kind of unique. So this might be that, but I'm hypothesizing here. Who knows what that circular object is, but it is a circular object. That's all I can say. The next one, Bloody Creek in Nova Scotia. We flew over that. They dammed it up so we can't actually see the circular effect, but it was right over here what happened, where it was. And some university in Nova Scotia did do a study. There are papers written about it, and I would like you to read them and make your own opinion. Again, we are fairly sure it's an impact, but we don't have firm proof. So this is kind of one of those maybe. But is it connected with the Younger Dryas effect? Again, that's the other hypothesis. And of course, up by Sept-Îles, 7 Islands in northern Quebec, on the northern shore of the St. Lawrence, is this circular structure within the St. Lawrence, Gulf of St. Lawrence, which is extremely circular. And again, it could be another charity shoal, or it could be an impact. Again, we have to drill. There's absolutely no evidence one way or the other if it's an impact or not. And finally, way up in Labrador, there's this one here in Meriwether. This was found during World War II. The pilots going places use that as a navigation waypoint. We find this circular lake, we know where we are. There has been a ground expedition there. Absolutely no impact evidence has been found. It could be a frost sinkhole, or probably not a kettle effect from the glacier, because it would have wiped everything out. So we still don't know what caused it. We can't prove its impact, but we can't describe what it is. Yep.
Just reading out a question from someone from a minute ago from Joe.
Sure.
How do they estimate the size of the meteor in relation to the rim?
Okay, mathematically they did with the energy. So they said, well, this is how much energy caused that bolide, that hole in the ground. And they then calculate, okay, how much energy would a object of X size at 14 kilometers a second cost? So they had to match the two, and eventually they came to a rough figure of a factor of 20. The crater itself is 20 times the size of the bolide that made it. That's the closest answer we can. Again, no absolute proof, but there is, papers written about it, so it's close. But yeah, Merriweather, when we flew over it again, a perfectly circular object within the gravel. How that happened, I don't know. And of course, it's bowl shaped. They did soundings of it. It's a bowl shape, just like a crater. Who knows? So we just left it. That is a mystery. So I'm going to leave you with two mysteries solved. It's now you're starting your career. Here's two mysteries that you have to look at for now. The first one again is the Younger Dryas. We just explained 12,000 years ago. Something happened. Now within this field, this red field here, are all these called magnetic spherules. And the hypothesis is it is caused by an impact on a glacier that caused that, an impact on some kind of evidence or element that caused that. We don't know yet, but they're all over the place. They're in Europe, and they're actually found some in Greenland now. So they are all over the place. And at the YD effect, 12,000 years ago, is this black mat. Now, I don't know if you ever heard of the KT boundary, the Cretaceous Paleogene boundary. It's worldwide, and it happened 60 million years ago, caused by the Chicxulub impact at the Yucatan Peninsula. And this, they hypothesized, caused the death of the dinosaurs, caused the death of the non-avian dinosaurs. The dinosaurs still flying all over the place. Side story, we have a little bird feeder, and we have a red squirrel that jumps onto it and eats it. And of course, the birds come, so I call it the dinosaur mammal battle. Kind of cool. But anyway, back to the craters. This black mat, below it is the woolly mammoth and the Clovis culture. There was a Clovis technology within North America that was very advanced. They had very, very fine arrowheads and so on. They're very successful hunters. We suspect the Clovis wiped out the woolly mammoth. And it took a very intelligent person to kill a mammoth, I'll tell you. But I would have fed him for months. But anyway, on that mat, below it is the culture. Above it, absolutely no signs of the culture. So there's your dividing line, the YD effect. That's a mystery to solve in the future. And the second mystery I mentioned, tektites. Tektites are the molten blobs that happen from a crater, from an impact, are ballistically thrown here, there, and everywhere. And there are various shapes. Around here, it's called the Astro-Asian field. There are piles of these tektites are found everywhere. But we don't know where the crater is. We know there was an impact. We don't know where the crater is. So that's the second mystery you guys have to solve.
We've got two questions in chat.
Yeah, okay, go for it.
So the first one, could you please tell us how the multi-ring basins form?
Okay, the multi-ring, sure. So if you look at the very first image, let's go. Let's see. Let's go. I'll go right back to the first image here. Dun, 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 dun. Dun, dun, dun. And I'm going to show you. I'll go out the hard way here. Only not gonna. That was a long talk, wasn't it? Here we go. So what happens at the very beginning? This is Tycho crater at the very on the moon itself. You look at the moon, and this is the most prominent crater itself. So just think of this here was a puddle of water, and a raindrop came down and went plop in the water. So what the water had a bowl-shaped crater from the impact, and then it collapsed on itself, and you had this little bubble coming up in the middle. The Tycho crater, that's that mountain hardened like that. On the Clearwater crater, we had these circular islands. That blob actually collapsed on itself and caused the islands around it. So getting into Clearwater here. There we go. That is the central peak, just like Tycho. The central peak came up and then collapsed on itself, caused those islands, and then solidified from there. So that kind of answered your question. Oh, yeah. Are there shadow cones on the impact? No, the shadow cones, they are only on very large impact craters. Now, on Brent, that is, several kilometers across. It is too small to cause a shadow cone. The Chub up in northern Quebec, I looked high and low for shadow cones there, absolutely. And then there tends to be a magic limit about something like 10 kilometers across where you start seeing shadow cones. But this is a very, very nebulous area. I don't think there's any firm quantity of a crater size that causes shadow cones. But all I can say is small ones don't have them, big ones do. And again, shadow cones are caused by the shattering effect of the impact, causing the rocks around to shatter in various spots. And the shadow cone effect is one of the effects from that energy level. So just these striations here you see at Charlevoix, and all the shadow cones in the example I have here are the striations only caused by the energy from an impact of a large impact, not small one, and or a nuclear explosion. So there we go, getting close. So the Younger Dryas effect, that's one mystery for you guys. And of course, the Australasian tektites. There has been an impact. We don't know where it is. We're still looking for it. So I'm going to leave you something at the end. I showed you an impact from Beringer. That was a pure iron impact crater, meteorite. And that is from, it's a differentiated object. Basically, it's been melted several times. And within an asteroid, the heavier elements sink to the center from gravity. And of course, you got an iron core. The asteroid got blown apart, hence the iron meteorites all over the place. And the iron meteorite that caused the Beringer crater was in fact iron. And then you have stony meteorites at the other end of the spectrum. There are, they're called chondrites, like that. They're stones that contain what's called chondrules. They are the original forming blocks within the solar system, and they're embedded within these meteorites, and a calcium aluminum inclusion. These are the oldest objects that were first formed within the solar system in these meteorites. So you have these stone meteorites that are chondrites, iron meteorites that have been differentiated, melted several times with the iron. So then between the two, you have an infinite variety of meteorites that are various mixtures of all kinds of stuff. And so you can write several PhDs in the different kinds of meteorites, basically, is what I'm saying. But I want to describe the Tagish Lake because this was very, very unique. This was formed at the outer area of the solar system. It's called a carbonation chondrite, and its own group basically is a very unique meteorite. And it is full of water, objects that were formed outside of the solar system. Basically, we call it the water snow line, basically. Anything past Jupiter solidified is full of water, and anything inside has been differentiated by the power of the sun is very low water. So these kinds of meteorites and the comets, we hypothesize that's where all our water came from. So this here is one of the oldest objects we've ever found. And this is my close-up in my little lab I've got. I call it my failure analysis lab. These might be microdiamonds, I don't know. But this is on this Tagish-like meteor right there. This is normal size print. And this is my little example of how close I can get to it. So it might be a nanodiamond, who knows? But it's my little project. So to conclude, you get these, we're actually, I don't want to scare you too much, but we're actually in a shooting gallery because there's comets and meteorites and asteroids flying all over the place. So Isaac Asimov just loves it. He said, how bright and beautiful a comet is as it flies past our comet. But does it? provided it does fly past. Yeah, go ahead.
You got another question in the chat.
Sure, yeah.
So what about mineralization associated with impact craters? PGE/C could be found with a big concentration, but how? Is it because of the radial faults?
I am not a geologist and I don't know. What about the mineralization associated to impact? Okay, within the impact melt, all I can say is that the impact melt is an amalgamation of the impactor and the bedrock and anything else that happens to be around. So after that, you'd have to read the papers. I won't even hesitate. I won't even try and answer that question, but it's a damn good question, I'll tell you.
I think Daniel's offered a bit of an answer.
Sure, go
just a
for it.
direct message.
Please,
to this one.
please.
So there's pseudotaculate breccia at other large impacts like Papagayi, Russia.
Yes.
And his personal project impacts with Napsis in Australia.
Okay. Yeah, Australia's wall-to-wall craters. I love it. Yeah. So, yeah. Actually, if you could email me that evidence, I'd really appreciate it. My email's on the bottom of my website. Just click on it and please, any information you have about that. My background is electronics, so I'm just doing this for fun. So, any other questions? I think, how about the computer? I think we got them all.
So far, we're caught up on the chat. Yeah.
Okay, so in that case, thank you for your attention. And again, if you have any other questions, I got my email out there ready to answer questions. Thank you very much. Love it. Time for you.
Okay.
Stop the recording here.